Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 13, Liquids. So as you saw with the chapter on solids, we're going to focus more on the physical aspects of liquids than the chemical aspects of liquids, though we will talk a little bit about the chemistry involved in some cases. So first we'll start by talking about what pressure is and how we look at pressure within a liquid. We'll then talk about the concept of buoyancy in liquid. This is a force lifting things up that are floating in or above liquids. We'll talk about how that relates to Archimedes' principle of displacement. We'll talk about what makes an object sink or float, both in terms of the buoyancy forces that are involved and the density of the liquids versus the density of the objects that are floating or sinking. And we'll talk about how that all relates to flotation in general and the buoyant force. The buoyant force is the force of buoyancy. We'll talk about Pascal's principle of hydraulics, and this is how force and area and pressure are interrelated with one another. And then we'll talk about surface tension, especially surface tension in water, and we'll talk about capillarity, which is also known as capillary action. So pressure. Pressure is a measurement of force divided by area. So it's force per area. How much force are you putting on? How much weight? How many newtons of force are you pressing over a certain space, a certain area that you're pressing on? And this can be used for pressure in gases. It can be used in pressure in liquids. So it has a lot of applications. And the general form is pressure equals force divided by area. So pressure depends not only on how much force you put, but how far that force is distributed. Is it all concentrated in a tiny area, or is it spread out? You can think about walking in a normal big fat pair of shoes, hiking boots, where the force is distributed over the large soles of your shoes, or you can compare that to the exact same force of your weight standing in stiletto heels, where your weight is pressed on tiny little heels that have a very small surface area, and therefore the exact same amount of force is now distributed over top of a very tiny area, creating a much greater pressure. So the units we use for pressure, since pressure is force divided by area, we use force units divided by area units. So newtons over meters squared. Meters squared would be our units of area. And we have a special name for that, named after Blaise Pascal, who was a pioneer in studying forces and pressures. He's also a famous mathematician as well. And so the unit is called the Pascal. And when we're talking about atmospheric pressure, the atmospheric pressure tends to be about 100,000 pascals. So we might use the kilopascal, which is 1,000 pascals. So 100,000 pascals is 100 kilopascals. Kilo just means 1,000. So those are the metric and SI units for pressure. But we also have a lot of other different units for pressure. We're not going to use all those different units. We have PSI, which is pounds per square inch. We might use the one that's listed here, pounds per square foot. These are imperial units from the imperial system. So you have an imperial force or weight unit, pounds, divided by an area unit, feet squared. But you might have inches squared. So pounds per square inch is what PSI is, and you probably heard of PSI. But there are a lot of other units, especially when we're talking about atmospheric pressure, which we're not going to talk about too much in this unit. Most of this is focusing on liquids, but atmospheric pressure also uses atmospheres as a unit of pressure, bars, torr, millimeters of mercury. There are a lot of different units of pressure, but these are the ones we're going to focus on for now. So pressure, think about pressure, it's the force per area. So if you spread out the area, you spread out where the force is, and the overall pressure will go down. And the perfect example of that is when you have somebody that's sandwiched between two boards of nails. Obviously, if you put a person between a board with only one nail sticking up and another board with only one nail pointing down, that would be pretty devastating to a human being, even without the cinder block sitting on top of the board. But once you spread that force out of the block and the weight of the board and the sledgehammer coming down on the cinder block, when you spread that out over many, many, many nails, even though each nail has a tiny surface area, it's a lot of different surface areas spread out over a wide range of space, and therefore someone can actually tolerate this kind of pressure if the force is spread out very wide. So it's the same amount of force, but a much larger area. So force divided by a large area will give you a small pressure on the person's body. And obviously you can compare this to the single nail. That would be horrible. So let's look at a simple example. When you stand on 1 foot instead of 2, the force you exert on the floor is the less, the same, more, impossible to determine. Okay, you're standing on 1 foot instead of 2. Is the force you're exerting on the ground any different? Do you still weigh the same? Yes, of course you do. So the force is exactly the same. Your weight has not changed. All you've done is distribute where the weight is pushing on the ground into a much, much smaller area, well, a much smaller area when you stand on only 1 foot, or when you just stand on the toes of 1 foot. You're just making the area smaller. You're not changing the force. Remember, weight is a form of force. So be sure to distinguish between force and force per area. That's what pressure is, force per area, force divided by area. Now, when you stand on 1 foot instead of 2, the pressure you exert on the floor is less, the same, more, impossible to determine. Well, you've cut your area in half. So remember, pressure equals force divided by area. So pressure is inversely proportional to area. Whatever you do to area, the opposite will happen to pressure. So if we stand on 1 foot, we have cut the area in 2. We've decreased it twofold. Therefore, the pressure will increase twofold, and we will have more pressure in this case. Right? Pressure, half the area, double the pressure for the same force. This is if we have the same weight, the same force. So an example of that would be a 120-pound woman standing on 2 feet, and let's say her feet occupy a total area of 0.4 square feet. I know that's a double use of the word feet, but her human feet are standing on 0.4 feet squared of area. And so she exerts 120 over 0.4, or 300 pounds per square foot. That's her pressure, because it's a force per area. That's pressure. But when she stands on 1 foot, she cuts her area in half. So now instead of 120 divided by 0.4, it's 120 divided by 0.2. And now her new pressure is 600 pounds per square foot. She's doubled her pressure. The force is exactly the same, but it's exerted on a smaller area. So let's talk about pressure in a liquid. And this is a little harder to comprehend than pressure in a gas, but pressure in a liquid is still force per unit area that the liquid exerts on an object. And that could be the liquid exerting on an object in the liquid or the walls of the liquid. So that's the pressure, the internal pressure. And it's depth dependent. So it's not volume dependent. Now this may seem a little weird, and let's explain what this means. It means the deeper you are in the water, so depth means here's the level of the water and how far down you are. And if the water starts here and you're going down, it's whatever the distance is between the top of the water and where you're looking at. That's the depth. It only depends on depth, not how wide the water is. Because when you're down below in water, the only thing that's important for pressure is how much weight is sitting directly above. And it's that weight that's directly above. It's not the weight all over on the sides. So it's not dependent on the volume. It's dependent on how much water is above it. So if you swim twice as deep, there's twice as much weight of water on top of you, and therefore you'll feel twice as much pressure, twice the force. You're the same area, you haven't changed, you've just gone deeper, and now there's a lot more water on top of you, more force, more weight. The force, or weight in this case, divided by the same area, the force is doubled, you will double the pressure. So in this case, if you look at this formula, P equals F over area, P is directly proportional to force. Pressure is directly proportional to force. Pressure is inversely proportional to area. And if you kept the pressure constant, you would see that the force and the area are directly proportional to one another. If you increase one, you'll increase the other if the pressure is constant. So be careful about your proportionalities. P is proportional to F because they're both numerator. P is inversely proportional to area because P is in the numerator, area is in the denominator. And if I rearrange this equation to read F equals P times area, then you will see that F and area are both in the numerator in that case, and they are proportional to one another. So pressure at the bottom of a 5-meter deep vat of water is the same as the pressure at the 5 meters deep in the ocean. Has nothing to do with how wide the water is. It's water straight above, so it doesn't matter how narrow it is. All right, so pressure in a liquid acts equally in all directions. Now, there's a little caveat to this. Yes, if you have a small object, there's a slight difference in the pressure at the top than there is at the bottom. There's a little more pressure at the bottom of an object, small object, but it's not that much difference in if the height of that object is not that big. So we're going to assume that that's minor for now. But the pressure around the object, pressure is going in all directions at every point with the liquid pressure within a liquid. And one example of that is the finding that when you're underwater, your head, no matter how you tilt it, because your ears aren't really that different in depth, even if you tilt them completely, the amount of pressure you'll feel hitting this direction will be about the same as the amount of pressure you'll feel in this direction. They're equal for equal height in the water. And the bottom of the boat is pushed upward by the pressure from the water around it. So it's always going to be pushing on whatever surface is in that water, and it's always pushing perpendicular to the surface. So on my head, it would be pushing this way, and at my angle of my head would be that way. Whatever is perpendicular to the surface of the object that's floating in the water or underwater, at least. The bottom of the boat, it'll be all these force vectors pushing around the bottom of the boat, adding to the various pressures that felt by the boat. And the pressure will act upward to push the boat up. And if you had a beach ball submerged completely, you would get pressure around it in all directions. Now this, it's not exactly true that it's equal in all directions, because the top tends to be less because there's less water pressure at the top than the bottom. But if the object is small enough and the top and the bottom are around the same depth, the actual pressure in all directions around that object will be the same. All right, so pressure in a liquid is independent of the shape of the container. Doesn't matter what the shape is. I said how much water is above, but above is kind of a relative term. No matter how weirdly shaped that container is, and if you look at the picture here with Lillian, the wife of our author, you see it doesn't really matter. The tops of each of those blue liquids are rising to the same exact height relative to the bottom of the container. And therefore, each of them will feel the same pressure at the bottom of each of those weirdly shaped containers. Doesn't matter what the shape is, it still has the same height of water above it. So depth, remember, depth refers to the distance from the top surface of the water to however low you're measuring the actual pressure at. All right? And the equation for this is that the pressure of the liquid is just equal to the weight density. Remember, weight density of water would be the number of newtons per cubic meter. So it would be a density that is corrected for gravity. All right? And then you multiply that by the depth. So what you notice here is that the pressure is directly proportional to two things: how dense the liquid is and how deep you are in the liquid. Those are the two things you're concerned with. That's it. So the water pressure provided by a water tower is greater if the tower is A, taller, B, holds more water, C, A and B, D, none of the above. Well, we've talked about this. It's the depth that's important. In this case, the depth means how high it is from the top of the water, the surface of the water, which is inside that top part of this water tower, down to the bottom where the water is coming out, where you're interested in the pressure. So it's only the height. It has nothing to do with how wide the thing is, how much volume the entire tower holds. So it's the height in this case, because height really is the depth of the water. And a narrow tower with a water level at 100 meters has exactly the same water pressure. The reason why we don't use narrow towers is they just don't hold that much water for the use of whatever town they're supplying to. All right, so pressure in a liquid. Water pressure acts perpendicular to the surfaces. This is what I was showing you before with my head, and you can see this with the triangle here. No matter what shape the object is, the water pressure will come in and perpendicular to that surface, and that will be the force that's felt, the force per area felt for that object. Now, also related to this is if you puncture the bottom of some container, or you have this giant water tower and you're letting the water come out, the water, since pressure is always perpendicular to the surface, when the water is released, it is also released perpendicular. So it will come out at right angles from whatever hole it is coming out. Now you'll notice in this cup, the walls are not straight up and down. They're slightly beveled. But the arrow of the vector of where the water is first coming out is slightly tilted down to match the tilt of the cup. So it's still perpendicular coming out of the cup. Of course, it'll fall down due to gravity, but initially that liquid will come out exactly at right angles from the hole in whatever surface you have, no matter what the angle of the surface is. And the greater the depth, the greater the pressure. We already talked about that, but that means that more pressure will mean the speed of the liquid at the bottom will be coming out much faster than the speed at the top. And that's why with this cup, you see that the liquid coming out at the bottom stays close to perpendicular longer because it's going out faster. It's just shooting out faster from the bottom than it is from the top. Why? Because it has more water sitting on top of it, pushing down. The pressure is on it to push out. All right, so let's talk about buoyancy. Buoyancy is the apparent loss of weight of a submerged object. Okay, what does that mean? That means when you put something underwater, the water is lifting it up a little bit. The pressure of the water is actually lifting it. And that pressure, that force that's actually on the object, because pressure is force per area, and that object will have a certain area, that force that's pushing up is called the buoyancy force, or the force of buoyancy, or the buoyant force. It has multiple names. All right, and it's oddly enough, here's what it's equal to. It's equal to the weight of the water, not the object, the weight of the water that's displaced by the object. Okay, what does that mean? That means when you shove an object in water, whatever part of the object is below the water, say you're floating it and only part of it's below the water, or it's sinking and all of it's below the water, whatever volume is below the water line, that's the amount of water you moved out of the way. That should be pretty obvious, right? You put some object in the water, water's moved out of the way by that object. If it's sunk all the way, its entire volume is displaced, the water is moved out of the way. If it's only floating, maybe part of it is below the water, and that much water is moved out of the way. The weight of the water that is moved out of the way, the weight of the water that is displaced, is exactly the force of buoyancy. That is the force in newtons pushing up. And we'll talk about where that even comes from in a second. So look at the object here on the left. You have something floating in the water, sitting. It's not actually floating. It's somewhere submerged in the water, but it's not already sunk. It's somewhere in the middle. It's actually between floating and sinking. And what you see are all these force vectors. This is the various forces, or you can pushing around the surface of this object. And what you'll notice is the force lines are always perpendicular to whatever the shape of the surface is. So the surface is curved, but the lines are always coming in exactly perpendicular to whatever curved surface it is. And the second thing I want you to notice is that the lines towards the bottom are longer than the lines at the top. In other words, the force at the bottom, there's greater force. That is because you're deeper on that object. The object at the bottom of the object is deeper than at the top of the object, so the pressure is greater on the bottom and the forces are greater on the bottom. And on the sides, they're exactly equal to one another because they're at the same depth. but they are in opposite directions. Now, the third thing I want you to notice is that the arrows on the sides will cancel each other out. Those are the same forces, but in opposite directions. So they'll be gone. Those are canceled when we look at net forces on the object from the buoyancy of the water. The forces on the top are in opposite directions of the various forces on the bottom, but they're not as big. So they'll partially cancel the forces on the bottom, but not totally. And what you'll end up with is a net force pushing up, and that net force pushing up we call the force of buoyancy, or the buoyant force. Now, is this the only force in this object? Well, no. The object has weight. There's also the weight force pushing down. And you know that there's some other force here besides the buoyant force. Otherwise, the buoyant force would keep lifting this object right up out of the water. So there must be some counter force keeping it in place. And that force in this case is weight. So buoyancy is always a battle between the buoyant force of the water, or whatever liquid it's in, or gas. We'll find out later. Gas will also work, but not as well. You have a buoyant force pushing up because of lower pressure at the bottom, higher pressure at the bottom than lower pressure at the top. So there's a net force up. But you also have the counter force down of the weight, and it's always a balance. Which one's greater? So let's look at some objects that have different densities. So for the same volume, total volume of the object, they all have different weights. Let's assume they have different weights. And from left to right, they get heavier and heavier for that same object. They're denser and denser. If we start in the far left container of water, we see it's up 1, 2, 3, 4 notches on there. The water's at 4 notches of there. And if we take something that is very, very light in density, like styrofoam, we put it on top of the water, a little bit will go in, but not a lot. So it doesn't displace much water. Why? Because it doesn't have to displace much water. To that water's weight that it displaces only has to be enough to balance the weight of the whole styrofoam block. So in this first block picture, only a little bit of water is displaced because that's all that's necessary to keep the block up. And when those two balance, when the buoyant force and the weight force are equal, the block won't sink anymore, and it will continue, it will float at that point. If we look at the second block, you see it's deeper. So this is a denser block. It's a block that occupies the same total volume, but more of it is below water. More of it has sunk below the water line. And that is because more of the object's volume had to go below water because it needed to displace more water volume, more water weight, in order for the displaced water's weight to match the object's weight. You had to displace more water. So this gets a little tricky and confusing. You were displacing water's weight by using the object's volume that's below the water. The object has a certain volume, it sinks. Whatever volume is below, we look at that volume, not of the object, but that volume of the water, and we ask, how much does that water weigh? What is the weight of that? And that is the buoyant force up. And if the object is floating, it will always be, the buoyant force up will always be the same as the weight of the object pushing down in order to keep it there. The third block is an object where all of its volume had to be below the water. In other words, it had to displace all of its volume in water in order to get enough water displaced to account for the weight of water that would match the weight of the object sinking down. So here we have a situation where they're exactly equal. The whole thing had to be submerged, and it might be right at the top, or it might hover somewhere in the water. As long as it's fully submerged, that's enough. Now, if the object is too dense, that last drawing, it doesn't matter how much water it displaces. It will never displace enough water's weight in order to balance its own weight. And what we find is, it turns out the math works out that if you look at the object, if its density is less than water, it will float. If it's the same as water, it will hover somewhere about that third block's picture. And if it's denser than water, it'll just sink. It will never be able to displace enough water because it doesn't have enough volume to displace enough volume of water to match its heavy weight, to displace enough weight of its water to match its heavy weight. I know it's a little confusing. Think about it. Okay, so the displacement rule. This is a little different from the buoyancy. This is just talking about the volumes itself. So this was something that Archimedes discovered about 300 years before BCE. And he noticed that when you put an object, no matter what the weird shape of that object is, into water, it will displace exactly its volume of water. Now, this may seem obvious to you nowadays, but that was not obvious to the people at that time. So if you had a weirdly shaped rock and you put it in the water, the amount of water that would be lifted up on the level, if you were able to measure it, that would be exactly the same volume as this oddly shaped object or rock or whatever this is. And you can do this in a couple ways. You can fill a container completely full of water, like it shows here, the bigger container here, and then drop an object in and just watch how much water is spilled into another container. That volume of water will be exactly the volume of the rock in this case. Of course, a much easier way to do this would be to start with a measuring device that has little notches on it. You can accurately measure the volume. So we use graduated cylinders in the lab, and you throw in your chunk of whatever, weird metal, rock, whatever can sink, has to sink all the way. So it has to be denser than water to do this. You sink it down there and it'll move the water level up. Well, that change in water level is exactly equal to the volume of that object. So if you have something really weirdly shaped and you want to know what the volume is, this is the easiest way to do it. There's no way you're going to be able to measure all the nooks and crannies and get an accurate volume calculation. This is ridiculously simple. You look at the before and after volume of water, take the difference, that's your volume. And this is the displacement rule that Archimedes came up with. And he came up with it because he was tasked by the local king to find out if a crown that was made for him was made of pure gold. Now, the reason why is he had given gold to the goldsmith to make a crown for him, the jeweler who made a crown for him. And when the crown was given back to him, the king suspected that the jeweler was a bit of a thief and that he had replaced some of the gold with other metals like silver. Well, silver is not nearly as dense as gold is, and therefore the amount of weight per volume should be lower if there's silver in there. Well, it's easy to measure the weight of something. That was simple. They could use a balance and just measure it. But how do you measure the volume of a crown with all these little nooks and crannies and things on it? Well, the story goes that Archimedes was sitting in his bathtub, and as he plunged his body into the tub, he watched the water spill out, and he suddenly realized what was going on. He jumped out of the tub. Yes, he was naked, that's the story, and he ran down the streets yelling Eureka, which is Greek for I found it, I discovered it. That's actually the motto of the state of California. And that relates to the gold rush, I found it. So Archimedes' principle of displacement of submerged objects allowed him to measure the volume accurately of the crown, divide the mass by the volume of the crown, compare that density to the density he knew for gold, and if they don't match, if the density of his crown is too low, he knows the jeweler stole some gold and saved it for himself and replaced it with cheaper metal. Well, in fact, he did. He reported to the king, but it's not known in the story what happened to the jeweler. All right, so this is just saying the volume on the right here, it's the overflow volume minus will equal the volume of the object. In the situation on the left, it's the extra volume that pops up. That's the volume of the object. All right, so a cuckoo measures a specific amount of butter by placing the butter on the bottom of a measuring cup of water using so they're putting butter on the bottom of the cup. They're putting water in, they've got a cup that already has water. They're putting the butter in, and they're watching the rise in the volume of the water. Is this the principle of buoyancy, the displacement rule, the concept of density, or all of the above? Well, yes, it involves concepts from all of these, but it's really the displacement rule. You're putting an object that's in the bottom in water, it raises the water up. You're displacing the water level from one level to another. It's simple displacement. So it's just you have a new volume level that's been displaced by the volume of the butter. Now, little note from me personally, I didn't write this question, but the fact is butter has less density than water. If you put butter in a cup of water that's already got water in it, butter is just going to float to the top. The only way to make this work is to get the butter to stick to the bottom of the cup and put the water and have the water in there already and see where the water rises to, and that's kind of awkward. There are much better ways to do this. All right, so buoyant force, where does it come from? Well, think about an object that's in water, and it doesn't really matter what the depth is in the water. The upward buoyant force is just going to be equal to the upward forces on the bottom of the object minus the downward forces on the top of the object. Remember, water pressure is always coming in perpendicular to the surface. On the bottom surface, that pressure is pointing up, and on the top surface, that pressure is pointing down. But the bottom surface is always lower. It has a deeper depth, so there's more pressure on the bottom pointing up than there is on the top pushing down. So there's always a difference. And if you look at these force vectors, no matter how deep this square or this rectangular object is in the water, the force pushing up from the bottom is always going to be greater than the forces pushing down at the top, because the bottom is always lower than the top surface of this object, no matter how deep you put it in the water. It's always the same difference, and you will see the same buoyant force no matter how far it is in the water, as long as it's fully submerged so that water is all around it, pushing on it in all directions. So this difference between the upward force from the bottom and the smaller downward forces from the top, that's equal to the buoyant force. And if the object is floating or hovering in the water, not sinking, that upward force will be exactly equal to the weight of the water displaced, which is the weight of the water that is the same, that has the volume of this box or the object. I know that gets confusing. So you're looking at the volume of the box. That is the volume of displaced water. You look at the weight of the water that is displaced, and that is the force upward. That is how it's calculated. If the object is completely underwater, you look at the whole volume of the box, the whole displaced water, the whole weight of that. If it's floating and part of it is above the water, you don't count that volume. You only count the volume below. But whatever is below, that volume of water, not of object, that volume of water will give you a weight of water displaced, which will be exactly equal to the weight of the object pushing down. The object will only sink as far as it needs to displace enough water weight to match its own weight. So larger objects by volume displace more liquid. I'm talking about an object completely underwater. A larger object will displace more water and therefore have more of a buoyant force pushing it up. All right, so how many forces act on a submerged body at rest in a fluid? 1, buoyancy. 2, buoyancy and the force due to gravity. None, in accord with the equilibrium rule, sum of the forces or the net force equals 0, or none of the above. Well, remember, the object didn't lose weight just because it's sitting in water. It still has weight. It still has a force down due to gravity, mg, all right, mass times gravity. But there is also that buoyant force due to the different pressure at the top of the object and the bottom of the object. So you have a force of buoyancy, buoyant force pushing up, and you have the force from gravity pushing down, mg. If the object is just hovering there in the middle at rest, the forces must be equal. Net forces must be 0. So we know it's at rest. That tells us immediately net force is 0. Net force at 0, that means there have to be opposing forces to stop the buoyant force. And that opposing force is the weight. All right. So rules on sink or swim, or sink or float, or neither. An object will sink when the weight of the submerged object is greater than the buoyant force. Okay, remember, you're always comparing the buoyant force to the weight of the object. Weight of the object's pushing down, buoyant force is pushing up. Whichever one wins, that's what happens to the object. If the buoyant force if the weight is heavier than the buoyant force, even if the object is completely submerged and it still doesn't displace enough water to match its own weight, it will sink. If enough of the material is below the water to cover itself, to displace enough water's weight to balance its own weight, it will float. So the buoyant force will equal the weight of just the water that's displaced by the floating object. In other words, the buoyant force is equal to only the weight of the water, the weight of the water that would have been below the water line for the object. So if an object is kind of halfway in the water, you only look at half of that volume below the water, and it's that water mass, water weight that you're concerned with. It's the weight of the water that would have been there. The weight of the water that would have been there is the buoyant force. That might be the best way to say that. So it's the volume of the object, not the object's weight, that's below the water line. You have the volume of the object below the water line. That's the volume of water that you're interested in, but you're not interested in the water's volume. You're interested in the water's weight that is displaced. I know that gets confusing. An object will neither sink nor swim when the weight of the entire submerged object is exactly equal to the buoyant force. When do you see that? You see that when the object has exactly the same density as the liquid you're putting in it. If you put an object that has a density of 1 gram per cubic centimeter in water, which has a density of 1 gram per cubic centimeter, the object won't sink or float. It'll hover somewhere in the water. We call suspended or hovering. So Archimedes, I told you about his principle. He lived in the 3rd century BCE, and he was interested in the buoyancy of not just of the displaced water. He was looking at buoyancy itself. So he worked out both the displacement rule and the buoyancy rules. Okay, they're related, but they're not exactly the same. So he noticed that the weight of the displaced water is the force that's buoying up. That's what we say. Buoying up, lifting up the object that's sitting in the water, or whatever fluid we're interested in. We don't count the volume of the object above the water line. You'll see I've circled each of the displaced volumes in each case. You're only interested in the water that would have been in that area. The weight of the water that would have been in that circled area. That is it. That is the buoyant force. We don't count anything above the water line. So this applies both to fluids like water or salt water or anything, liquid mercury, but it also applies to gases. When we talk about hot air balloons are less dense than the air around them, and then they end up floating. Well, that is because of the buoyant force of the air, which is not nearly as great as buoyant force of water, but it's enough to keep a giant balloon up in the air. And we'll talk about that in a moment. So Archimedes' principle, which is talking about buoyant force, the force of buoyancy, also leads us to the concept of apparent weight. Okay, the apparent weight is the weight out of water. In other words, the true weight minus the buoyant force. In other words, if you weigh 150 pounds and you had a bathroom scale in the water and you were able to weigh yourself in the water, and you found you were only 100 pounds in the water, that would be a buoyant force of 50 pounds. That would be pushing you up. Okay, so it's your true weight minus the buoyant force that's pushing you up. Remember, weight is going down, buoyant force is going up. The difference will be what you appear to weigh, your apparent weight. So here's an example of apparent weight, but they used masses instead of weights. If you want, you can convert this to weights in the metric system. Just multiply 3 kilograms by 10, and you'll get the number of newtons. So this would be a 30 Newton block, is submerged in water. It has an apparent mass of 2 kilograms, so that's an apparent weight of 20 newtons. Okay, it doesn't matter which one we use. Well, let's keep it as newtons to make it a little more straightforward. So we got a 30 Newton block. We put it in water, and we can hang it from a spring scale, so we know what the weight is of the block before we put it in water. It's 30 newtons. We dip it in water, and suddenly it only weighs 20 newtons. 20 newtons. Well, where did that extra 10 newtons go? That's the buoyant force. And we can actually measure that, because if we took this exact same weight and put it in a container that's filled to the brim with water, and we dropped it in there, the water that would be spilled out would be that 10 newtons of displaced weight of water. So you can actually measure how much water is literally physically displaced into the other container, and that would be your difference. I notice in here that the way this is displayed here, it actually switched the numbers 1 and 2 in the version here. I'll have to fix that later, but that might be from the original text. Okay. So next question: which of these 3 metal blocks will experience the greatest buoyant force when submerged in water? Okay, so they're all metal blocks. 1 kilogram of lead is PB. 1 kilogram of aluminum, Al. 1 kilogram of uranium, U, or all of them the same. So we want which one has the greatest buoyant force. The greatest buoyant force is not calculated by anything related to the weight or the mass of the object. It's the volume that the object displaces in terms of water and how much that weighs. Well, they gave you a table of densities here, and if you look at the table, you can see that aluminum has a density of 2,700 kilograms per meter cubed, or 2.7 grams per cc. Lead is much higher, 11,340, and uranium is almost double that, 19,050 kilograms per meter cubed. All right, well, you don't need to use these numbers, you just need to realize that these all have very, very different densities. So what does that mean? That means 1 kilogram of aluminum will be a certain size, but lead is much denser. So you don't need the same size to make 1 kilogram. You would have a smaller block would be 1 kilogram. And aluminum would be an even smaller block than that because it's so very dense. You only need a little block to have 1 kilogram. You need a bigger block of lead to have 1 kilogram. You need a really big block of aluminum to have 1 kilogram. So that means the aluminum will be the biggest block in that water. All of them are metal. They're all denser than water. They will all sink to the bottom and displace their entire volumes. But aluminum has a bigger volume because they're all the same mass. So this is a little tricky. You have to think about masses, not... you have to think about how the same masses means different volumes in this case. So they have different volumes. The one that will displace the most water is the aluminum. It will displace the most volume of water, which means it will displace the most weight of water and therefore have the greatest buoyant force. So here they are, the 3 blocks, so you can visualize them. The aluminum is going to be much bigger than the lead. The lead will be about twice as big as the aluminum, as the uranium almost, and then with no water at all. And because the aluminum is displacing so much more water, it has a greater buoyant force. None of them float because none of them have a buoyant force that's greater than their own weight. So that is why they sink. Also because the density of each of these is much higher than water. Water would be 1,000 kilograms per meter cubed. So aluminum is 2.7 times denser than water. Lead is over 11 times denser, and uranium is over 19 times denser. So they'll all sink. So the 3 metals are all denser. They'll all sink. They'll all displace their full volume. But lead and uranium are very dense, so they'll occupy smaller blocks for 1 kilogram than the aluminum. Aluminum has the biggest block. It will have the biggest displacement of water, the biggest weight of water that's displaced, and therefore have the greatest buoyant force. When a fish expands its air bladder, the overall average density of the fish, what? Decreases, increases, remains the same, none of the above. Well, let's talk about what an air bladder is. An air bladder is essentially a bag. It's an organ in a lot of fish, maybe most fish, that can expand with air or shoot out the air. Okay, and what it does is it expands it with air to change its overall density. If there's more air that's occupying its body, it's making it bigger, and therefore, with the same mass, the air is not adding that much mass to the fish, but it is adding much bigger volume. You can think of it as just expanding the body of the fish. It will make its overall density go down because the mass is now divided by a bigger volume. Density equals mass over volume. And therefore, the density will decrease. So gas is much lower density than water. When you expand it, the volume, which is gas, will lower the overall density. You're increasing the volume, but not increasing the mass. increase volume, volume and density are inversely related. So you increase the volume, the density goes down. And therefore, the fish can do what it needs to do. Now, I will tell you, fish do this because fish and submarines like to maintain neutral buoyancy. They always like to keep their buoyant factor, their buoyant force exactly the same as their weight. And that way they can move around the way they want inside the water. All right, when a fish makes itself less dense by expanding its air bladder, so it's gotten bigger, its density has gone down, the buoyant force on it, A, decreases, B, increases, C, remains the same, D, none of the above. Well, let's think about this. Yes, it's making it less dense, but more importantly, it's making it bigger for the same weight. Well, bigger means it's displacing more water. More weight of water is being displaced, and therefore the buoyant force will go up. Remember, another way to think about it is you decrease the density, it's less dense than water, or it's less dense than it used to be, it'll start moving up. Okay, it may not move up all the way to float, doesn't do that until the fish dies typically, but it can move its buoyancy up by doing this. So the larger expanded fish will have a larger volume, therefore a larger weight of water is displaced, and the buoyant force is that displaced weight of water. All right, when a fish decreases the size of its air bladder, so it's pushing out that air from the bladder, it's getting smaller, the average density, the overall average density of the fish decreases, increases, remains the same, none of the above. Well, the fish isn't getting any less massive, it's just getting smaller. So the same mass divided by a smaller volume, so volume goes down, density will go up, increase. So they're inversely proportional. So when it decreases the air bladder, the volume of the gas is lost. The fish gets smaller, it's more dense, density goes up, all right? And the object's overall density is less than the density of the fluid, it'll float. We're not talking about the fish necessarily, but that's true for any object. Okay. When a submarine takes water into its empty ballast tank, so this is just like the air bladder in fish. Its density, what? Decreases, increases, remains the same, none of the above. Well, you're not changing the volume. The volume of the submarine stays the same. These are tanks that are already on the ship, but you are adding more mass to the ship when you're adding water to the ballast tanks. You're making the submarine heavier for the same volume. So now you're increasing the mass without changing the volume, and that will increase the density. So you put water in there, the density will increase. Now, D equals M over V, you're increasing the M without changing the V, you're going to increase the D. D and M are proportional, D and V are inversely proportional. When the submarine expels water from its full ballast tanks, its density decreases, increases, remains the same, none of the above. Well, it's getting rid of the water, it's getting rid of the weight, its volume is staying exactly the same. The submarine's not changing volume, but it's losing mass. Lower mass, lower density, decreased density. They're proportional. Mass and density are proportional. Volume and density are inversely proportional. So again, the same thing, M is down, D is down. And this is how a submarine can increase its buoyancy in the water. The submarine is always trying to make its buoyancy exactly the same as its weight. It's always trying to be in a neutral position. It doesn't use this to float to the top, or it doesn't use this to sink to the bottom. It uses this to kind of hover in the middle, and then the engines and the various other equipment on the submarine will actually move it around up and down within the water freely. But the buoyancy is controlled with these ballast tanks to always keep it even keep its overall density the same as the water's density, so that it can really maneuver any way it wants in the water at any time. All right, so principle of flotation. Why ships can be made of steel. All right, so we've already talked about buoyancy in water. Let's talk about what this means for making ships out of materials that are much, much denser than water. Okay, a floating object will displace only the weight of fluid that is equal to its own weight. Well, if we have a solid block, a 1-ton block of metal, and we just put that in the water here on the left, it'll just sink right down to the bottom. It doesn't have that much volume. It's very dense. its volume can only displace its volume of water. And the weight of water in that volume is a lot less than the weight of the object. It's never the buoyancy is never going to be matching the weight of this heavy block. It has a very high density, and so the weight of that volume of metal is going to be higher than the weight of that volume of water, and therefore it will sink. It will have a buoyant force, but it's never enough to keep the thing up. But if you take that same metal and you pound it down into a giant boat that now is maybe really long and really wide, but it's still made of the same exact metal with the same 1 ton of metal, now it can displace a much larger volume of space. It pushes much more water out of the way, and as a result, it has a much larger buoyant force. This extra volume here, where it says larger volume, this would have been filled with a really large volume of water, which is enough to account for the mass of the iron in the boat. Why? Because if you look at the average density that's below the water, most of it's air. Some of it's metal on the sides, but most of it's air. And when you average it, the average density of that whole thing is going to be less than water, and it will float. So the volume of just the iron is the same in both the block and the boat. It's just when it's a solid block, its density is much higher. Its average density is much higher than when it's spread out into a giant boat with air filling that boat. That has a much lower overall density, and therefore it can displace much more water weight and keep above the water. The reason a person finds it easier to float in salt water compared with fresh water is because in salt water, A, the buoyant force is greater, B, a person feels less heavy, C, neither, D, none of the above. I think C and D are kind of the same, but I didn't write this. Well, let's think about this. This is a little tricky. Remember, salt water is denser. Okay, that is true. Salt water is going to be denser because there's salt in the water, and the salt makes it denser. If you've ever been in the ocean, it's a lot easier to float than when you're in a swimming pool. And if you've ever been in the Dead Sea, which is filled with salt, it's almost impossible to sink in the Dead Sea. I floated there. You can actually float in about a foot and a half of water. You can float your entire body in a foot and a half of water. It's amazing. You'll never experience anything like that. But here's the thing. Neither of these is true. Now, you might say, well, wait a minute. The buoyant force should be greater. It's salt water. The water you're displacing is heavier. It should be greater buoyant force. But here's the trick. Yes, it's denser. It's about 2 or 3% heavier for the same volume. So you're displacing heavier amounts of water, more buoyant force. But that's only if you went all the way underwater. You only need to sink enough to match your weight. And if you were floating before and you were floating after, each time the part of your body that was below the water was displacing exactly enough of that type of water so that the weight of that water matched your weight. Yes, if you're in salt water, you won't float as deep. You won't sink as deep, all right? A person floating in the salt water will float a little higher in their body. They won't be sunk down in the water as much because it doesn't take as much volume of salt water to make up enough weight of salt water to match your weight. Whereas if you're floating in fresh water, water with no salt in it, you have to sink a little bit deeper in order for that weight of displaced water to match your body weight. I hope that makes sense. Think about it for just a second. But the amount of water in each case will be different volumes, but they'll be the same weight, your weight. All right. On a boat ride, the skipper gives you a life preserver filled with lead pellets. When he sees the skeptical look on your face, he says that you'll experience a greater buoyant force if you fall overboard than your friends would, who are wearing styrofoam-filled preservers. A, he doesn't know his buoyancy physics. B, he is correct. Well, oddly enough, he is correct. But remember, I told you, it's not important what the buoyant force is when you're worried about sinking or falling. It's the difference between your weight and the buoyant force that's important. The second he gives you a lead vest, you will sink more, you will displace more water, Absolutely. So your buoyant force will be greater. The problem is you also weigh a lot more, and the new extra added buoyant force cannot compare to the extra added weight. You've made your whole body denser on average. So even if you sink completely underwater, yes, you have a much greater buoyant force than the other people do, but you also have a much, much greater weight than the other people do. And those two can't compete, and you will sink and you will drown. So obviously we don't fill life preservers with lead. All right. You place an object in a container that is full to the brim with water, right up to the top, on the scale. Okay, you're measuring the weight of the water on the scale. And then an object floats, but the water spills out. So you put an object in the top and it spills out. How does the weight of the object compare with the weight of the water displaced? In other words, the water that went into that side cup. The weight is less than the water displaced. The weight is equal to the water displaced. The object's weight is more than the water displaced. We don't have enough information. Well, by now I think you realize whatever is displaced must be exactly equal to the weight if it's floating or if it's hovering. If it's sinking, it's not going to always match. And this is a principle illustrated by a really unique device in Falkland called the Falkirk wheel. This is a giant wheel. It's a little hard to tell what that is, but you might be able to see in the bottom right some structures there where doors and windows in there. But this is a giant object that will carry a boat. These long caissons, these kind of long cups that are on there on this giant wheel that's rotating this way, they actually hold an entire boat. So a boat will sail into there, but these things are already filled with water. So when the boat sails in, it only displaces its own weight in water. And the other one is on the opposite side of this giant wheel, and they're turning end over end on this. So you have a boat here and a boat and a boat here, or just water here and a boat here. It doesn't really matter. They weigh exactly the same, so almost no force is necessary to rotate this thing. And the reason why they rotate this is a connection between one canal that's at a low level and a higher canal that's at a much higher level. And you have this giant wheel that allows a whole boat to be lifted up with almost no effort because the balancing weight on the wheel, they match each other. So it only takes a little motor to rotate the whole wheel. It's always balanced, always has the same weight. And I'll leave this to you to click on the link and watch it. This is showing you a stop action version of this wheel. On each of these arms, there's a caisson that's filled with water, and it might have a boat in it or it might not. But it makes the rotation very easy as a result. And it's the only one in the world like this in Scotland. It is. Okay, so denser fluids will exert a greater buoyant force on a liquid. So in other words, if you're in salt water with more density, you might displace the same volume, but that water weighs more because it's denser liquid. You can imagine if you had mercury, if you were able to displace a certain amount of mercury, it would be even more weight that you displace because mercury is so incredibly dense. It's about 13 times denser than water. So ships float higher in salt water. Why? Because they don't have to sink as deep to displace enough weight of water to match their own weight. Because the water they displace is heavier than if it was just fresh water. Salt water has a slightly higher density, but it's enough to make a difference. All right, so Archimedes' principle is not just for water and liquids and fluids. Well, fluids is a general term that means liquids or gases, but it's also for gases. And we can apply Archimedes' principle of buoyancy to gases like the air or other gases. Well, let's talk about the air. The more air an object displaces, just like water, and we're looking at the weight of the air displaced, is the buoyant force of this balloon. Whatever volume this balloon occupies, that's the volume of air that's been pushed away. That's the weight of air that's been pushed away, and that force is what's lifting the balloon. So the larger the balloon, the more buoyant force on it. A larger balloon will work better than a smaller balloon. A less dense balloon will work better than a more dense balloon. So if an object displaces its own weight exactly, right, there's no floating all the way to the top of air. We don't do that. It would hover in the air. So if its buoyant force is exactly equal to the weight, well, that's that middle place, and it could just float. And that's what happens with these balloons. They get to a point where the weight, the force of gravity, F sub g, is exactly equal to F sub b, the force of buoyancy. And at that point, they can just use other ways of moving across the sky or gently moving up and down, but essentially they can hover anywhere in the middle of the air. So an object, if it displaces less air than it weighs, the less weight of air, it will descend. So basically what this means is these balloons have to have an average density. The whole balloon has to have an average density less than the density of air around it, okay, so in order to hover up. If you sit reading this presentation, is there a buoyant force acting on you? No, as evidenced by the absence of lift. Yes, due to the displacement of air. Well, you're sitting in air. There's air pushing on you. The air pushing on the bottom of your body is more force. There's more force than the air pushing on the top of your head because it's denser at the bottom of your feet, and therefore the pressure is higher, and therefore you will experience a buoyant force. Is it much? No, it is not much at all. But you will experience a buoyant force just as if you were in water. It's just a much, much smaller. You're displacing a certain weight of air, but air doesn't weigh that much. It doesn't have a high enough density, so you're not displacing a lot of weight of air. It turns out the average person is displacing about 0.8 newtons of air. This works out to about 3 ounces, right? So much, about 1/6 of a pound. So when you weigh yourself on the scale, you actually weigh 1/6 of a pound more than you think. It's just the air is lifting you up. An object floats or sinks depending on what? Okay, it depends on the volume of the object that's below the water line. Whatever's below the water line, we're concerned with that much volume, and we're concerned with that much volume of water and how much it weighs. So it's the weight of that displaced volume just below the line. If it's all the way under the water, it's all the volume. And then we compare that weight, because that weight is the buoyant force, we compare that to the actual weight of the object. All right, so if the weight of the object is less than the buoyant force, right, so pushing down, but the buoyant force is really strong, you're going to float. The weight of the object has to be less than the weight of the water that would have been there. 3 rules for flotation based on the density. These are really easy. If the object's denser than the fluid, it'll sink. If it's less dense than the fluid, it will float. If it's exactly the density of the fluid, it'll hover somewhere in the middle, what we call suspended or hovering. Okay, it's also known as neutral buoyancy, though I won't quiz you on that. That's a term I threw in there. Okay, and this, like I said, is what fish do. It's what submarines do. All right, 2 solid blocks of identical size are submerged in water. All right, so the key here is they're the same size, not the same mass as we saw before. 1 block is lead, 1 block is aluminum. Which one experiences the greater buoyant force? Well, remember, buoyant force is based on the displaced weight of water. These are both metal blocks that will sink in water. And therefore, they will have exactly the same buoyant force because they displace exactly the same volume of water and exactly the same weight of water. So because the water volume is the same, the water weight will be the same of the displaced water, and therefore they will have exactly the same buoyant force. So let's talk a new topic with pressure and water, and it goes back to a formula right from the beginning of this lecture, Pascal's principle. Blaise Pascal from the 1600s. He was a brilliant physicist from France. He was a mathematician. He was an inventor. He was a philosopher. He was a theologian. He did a lot of things. He was unbelievably talented in a wide range of fields. And what he realized is that when you have a liquid and you apply a pressure to one side of the liquid, the rest of the liquid will feel the pressure everywhere. So it doesn't matter where you put the pressure, the same pressure will exist all the way through to the other side, undiminished. All right? Now, yeah, there's some variation with depth, but we're not going to talk about that right now. Since we're looking at the same depth in this picture of the pressure in and the pressure out, they're roughly the same. They're virtually identical. And this can work for fluids of all kinds. That means both liquids and gases. It's especially important with liquids, though, for what we call hydraulic devices. So hydraulic presses or hydraulic lifts take advantage of this this discovery that pressure in is always the same as pressure out. Why is this useful? Well, remember, if you've got something where you can put a certain amount of pressure in, you'll get the exact same pressure out. But pressure equals force divided by area. So if you have one force in one place with one area, and you change the area in the other part, you will have the exact same pressure, but you will have a different force because it's the ratio of force to area, which is pressure. So if we look at this diagram here, we've got this liquid-filled device that has a small area end on one side and a large area end on the other side. And what it's showing is a 10 kilogram mass on one side and a 500 kilogram mass on the other. Well, let's just convert these to newtons, so we're dealing with force, which is weight, okay? All I did was multiply them both by 10 and turn the kilograms into newtons. So now we have 100 newtons on the left, pressing on a very small area. Well, 100 newtons divided by area A produces a certain pressure. That's the pressure. It's force of that little weight over the little area. But pressure is the same on both sides. If I increase the area tremendously, I have to increase the force also on that area. And as a result, because I increase the force, I increase the area. I increase the area, I increase the force. And that's a direct consequence of this formula. If I rearrange the pressure equals force over area equation to look like the one on the right, force equals pressure times area, you'll notice if pressure is the same, force is directly proportional to area. If I bump up the area, I will bump up the force as long as P is the same. And Pascal says, hey, P is the same on both sides. Can't change that. P is the same on both sides, so therefore, if one side has a much smaller area, I need a small force. Big area, I'll generate a big force. So the ratio of those two is going to be the same, and that's why P is equal to one force over the area or the other force over its area. And this is a great way to amplify forces with the constant pressure. So if you exert a pressure on the left side of this piston, you can generate an enormous force on the right side of the piston. You put a 100 Newton load on the left on an area A, and you have an area that's 50 A on the other side, you will generate 50 times the 100 Newton force that you put on there. And this is the way hydraulic systems work, hydraulic presses work. So the input piston must move, it will have much less force. Well, how do you get away with that? How do you get away with a little bit of force generating a lot of force? Well, the difference is that piston on the left has to move a lot further deeper to make the piston on the right move a little bit up. That's where it comes out. And that's how it balances in terms of conservation of energy. Because remember, force times distance, how much it's pushing down, has to be force times distance. If we're pushing down over here, we still have to have the same amount of work being done, or energy. The energy input has to equal the energy output. There's no way around that. And the way you get around that is by pushing the 100 newtons much deeper to make the 5,000 newtons go up just a little bit. So, application for gases and liquids seen in everyday hydraulic devices. They're used in construction. They're used in auto lifts and service stations. Anytime you put your car up on a lift, that's what's happening. You've got an air compressor that's pushing liquid down a long, thin tube, so that same amount of pressure is over a very small area, which means it will generate a large amount of force on the large area on the other side. And that large area is attached to the part that lifts your car up, and that's the output piston. So the air compressor uses pressurized air, transmits its downward force over a long distance, pushes it down, and then your car lifts up a little distance in relation to it. And but in the process, you don't need a lot of force to raise something that's incredibly heavy, right? Because the force will be proportional to the area if the pressure is the same. And in this case, pressure is the same. That's Pascal's principle. So the oil will transmit the pressure. This is actually filled with oil, not with water. And so that one arrow of force on the left becomes many arrows of force on the right pointing up for the outward piston. So it's a great way to amplify force by taking advantage of this constant pressure and taking advantage of the fact that you have to push a lot further distance on the left than you do on the right to get it. So those balance each other out, but you end up with this mechanical advantage of force. So in a hydraulic device, like steam shovels and various other big construction equipment, the input piston, it's impossible for the A, input piston to move further than the output piston. B, force output to exceed the force input. C, input speed to exceed the output speed. Or D, energy output to exceed the energy input. Well, the input piston, we know, has to move further than the output piston in order to balance the energy in and the force at the work out. They have to be equal. So you have to put a lot more work on the left side where there's no force. The force output to exceed the force input. Well, that's the whole point of this device, is to make the force output exceed the force input. So it's not B. The input piston speed to exceed the output piston speed. Well, the input piston has to move a lot further in the same amount of time that the output one. So the input piston speed has to be faster. It's moving a lot further in the same amount of time. And D, the energy output to exceed the energy input. Well, that is definitely impossible. That is a violation of the conservation of energy. We know you can never have the energy output be different from the energy input. And if you're losing energy in the form of heat, your energy output will never be even as great as the energy input. You'll never reach it, right? Even the best machines, the output will always be a little bit smaller than the input. In theory, they could be equal. That's the best you can do. So the input piston uses less force, so it has to do greater distance and therefore move at a faster speed. The hydraulics use different areas, so the output force always exceeds the input force. All right, so let's talk about another completely different topic, surface tension. Surface tension is the contractive tendency of surfaces of liquids that's due to the surface tension. So what does that mean? That means when you have liquid, it will tend to pull on itself in order to make a stiffer surface over the top of that liquid. So an example of that would be water. Water has excellent, very high surface tension, and this is because the force is in water holding it together. It's water attracting other water forces, and as a result, making this tight, almost like a skin on the top of water. We don't usually notice it, but small insects will definitely notice it. A lot of insects will be trapped in water because of the surface tension. Some insects, like the water strider family of insects, they take advantage of it, and they can actually walk along the surface of water without sinking in because they take advantage of spreading out on this. And you can actually see the water kind of dipping in where their feet are contacting the surface. You can see surface tension if you take a cup and fill it with water and put a little extra water. It's a little hard to see where the arrow is pointing, but that water level is above the cup, and that's because the surface tension is holding the water together. It's contracting and pulling it in, trying to minimize the surface and making it almost like a tight skin on the top. You see examples of surface tension when you dip a paintbrush into water or even paint. You dip it in, the brushes may be separate, and when you pull them out, they're pulled together by the cohesive forces of the water pulling against each other. So surface tension has other manifestations in nature that you'll see. Raindrops, when they fall, I mean, these are on a spider web, you can see it, but when raindrops fall, we always tend to draw them as teardrops. But normally, raindrops are almost spherical. They're a little elongated because of the air resistance, but they're nearly spherical when they drop from the sky, and that's because the surface tension is pulling all parts of it into a sphere. The idea is they are trying to minimize how much of the surface, how much of the area on the outside is there. Most the molecules are all being pulled into the center, so all the molecules of water are trying to be in the center. Nobody's trying to be on the outside, and as a result, they're trying to have the least surface area possible. Well, the shape that has the least surface area for a certain volume is a perfect sphere. Bubbles do the same thing. This is surface tension of the soap molecules interacting with each other to kind of pull themselves into a sphere as well. So surface tension is basically the result of forces between water and water, or whatever liquid you're talking about. They're attracting each other, and when you have forces between similar molecules, that's called cohesion. Co meaning with itself, it's hesion, so it's attraction to itself. And if you have water molecules that are below the surface, shown in the bottom star of vector arrows here, they're being attracted by all the water molecules all around them in all directions. But if they're near the surface, they're attracted by all the water molecules on the sides and the bottom, but there are no water molecules on the top. And as a result, there's this net force pulling the top surface water molecules down under. And so they're being pulled under, but every time a molecule of water is on the top, it's being pulled down by the surface tension. And as a result, in order to best prevent this, the object will form a curve, the liquid will form a curve in order to minimize its surface area. And that curve results in the surface area, the surface tension that we actually see on the surfaces of liquids like water. It's the tendency to pull the molecules from the surface into the body of the liquid. Okay, so let's look at some factors that affect surface tension. The most obvious factor would be the type of liquid. Water is excellent at creating surface tension, and that's because water loves to interact with other water molecules in bonds that we refer to as hydrogen bonds. We won't get into the details of what hydrogen bonds are. We talked about some of the weaker bonds that I said were van der Waals bonds in the last section. And van der Waals bonds are a number of different types of bonds. They're all weak in comparison to things like covalent bonds and ionic bonds. But of the weak van der Waals bonds, the strongest of those is called hydrogen bonds. And water will form many, many hydrogen bonds with each surrounding water that's floating around it. So it really goes a long way to holding water together and creating this surface tension. Now, there are other molecules that are not quite as great. Oils don't tend to be nearly as cohesive and therefore have less surface tension. You can also mix things with a liquid to lower surface tension. If you interfere with the interactions, the cohesive interactions between the same molecules, by having other interactions like adding soap so that the soap forms interactions with the water to block some of the water-water interactions, you can interfere with these hydrogen bonds by forming different hydrogen bonds with the soap and therefore lowering the surface tension of the water. And then temperature is one of the easier things you can do. If you heat water up or any liquid up, the molecules move faster and they're less likely to interact with these hydrogen bonds or other van der Waals interactions or other cohesive forces that will keep the molecules together. They're just harder to do that if they're all moving around which way because of the high energy, because of the higher temperature. So higher temperature always will have a lower surface tension. All right. So related to surface tension is a concept called capillarity, more commonly known as capillary action, which you may have heard of. In capillary action, it's the rise of liquid in a fine hollow tube or in a narrow space. And what that means is liquids like water will start to rise up inside the tube. Well, what's actually happening here is instead of just cohesive forces where water is attracting water to make these tight surface connections to make surface tension, you can also have water interacting with other things, in this case, glass. And water interacts with glass with very strong interactions. Many of them are hydrogen bonding interactions or similar to hydrogen bonding interactions, and they're quite favorable. And as a result, the water will be attracted to the glass and actually rise up the sides of the glass. And if you have a glass tube sitting in water, you will see the water rise up along the sides due to these adhesive forces, adhesion. So cohesion is water to water or glass to glass or whatever to itself. Adhesion is something to something else. So water to glass in this case. And the adhesion in this case between the water and the glass is actually stronger than the cohesion between the water and the water. So you see this rising up along the surface of the glass itself. Surface tension will still cause the film on the surface to contract, and you'll end up with these curved surfaces called meniscuses, but it will rise up the length of the tube. And if you have narrow tubes, that's more glass for all the water to reach, and you'll end up seeing higher rises in the liquid up the center of the tubes. So the force of the surface tension balances the surface tension, and the capillary action from the adhesion balances out the weight of the liquid that's pulling it down. So it'll rise up a certain amount because of its cohesive forces and its adhesive forces to the glass, but eventually those forces will be balanced by the weight of the water that you've lifted up out of the capillary and stopped there. So the height of the capillary rise, the amount that it goes up, is really dependent on the density of whatever liquid it is. So if you had a denser liquid than water, you'll get less rise up because it's heavier weight that you're fighting against to rise up these tubes. And narrower tubes just mean more surface area for the liquid to grab onto and rise up. So you have more adhesion along the sides, pulling it up against the force of gravity. So the lighter, the denser the liquid, the higher the rise. The narrower the tube, the higher the rise. And capillary action can be seen not just with water. You can see it with non-polar greasy things like oils and waxes rising up wicks from candles. That's what's going on. Capillary action is pulling the liquid wax that's been melted by the flame, but it's been heated up enough that there's liquid wax that rises up the wick, and then it's the liquid wax that's vaporized to vapor wax, and then that's the vapor that actually burns to create the flame. So it's not the solid, it's not the liquid that rises up the tube, it's the gas that's burning, but it's the liquid that actually brings it up the wick to be burned by the flame. So water can also be transported in pores of not just glass capillaries, but in the pores of small primitive animals like sponges. Each of these pores acts like a capillary tube. And paint on brushes. The spaces between each of the strands, each of the hairs on a paintbrush will act like a small space for capillary action to pull the water or the paint or whatever liquid is being dipped in up the sides of the brush fibers themselves. So you get capillary action in that way as well. And with that, we'll stop here. Thank you very much.